All right, got some entertainment here. Uh, Hello, everybody. I'm ahead of time just a little bit here, or just exactly on time for us, because we're a little behind schedule. I was thinking about it, I was taking a look at the syllabus, and I'd really like to finish up the membrane stuff and even get on to disinfection if possible for you today. Try not to do that so that we can do it together in class, get live questions and everything, but just letting you know today I'm going to go a little quick, see if we can catch up with finish out the membrane stuff. We already did the exam recap and really get into disinfection at least a little bit today, which means we've got like a lecture and a half worth of slides to cover, and I'm going to get right to it. Okay, so we have fall break Thursday. Hope you enjoy that. And next week we'll do some finalizing prep for the exam. The week of the exam too, I'll be out of town, so I've got one grad student will give you the exams. She'll be here. Her name's Erlorm. And then on the Thursday of that week, I have another one of my grad students will give you a guest lecture on some advanced topics of this disinfection, chlorine kind of stuff. It'll be a good connection between the drinking water and wastewater. Sorry, let me get this anyway. It'll be a good connection there too, because we can actually, we do actually use disinfection for wastewater, but we're covering it kind of in the drinking water context today and next time. And so he'll give you kind of a bridge there for that. Okay, so get this out of the way and we'll get going. You're still welcome to pause me if you have any questions, want any clarifications. Definitely welcome that, but I will be moving a little quicker today. So last time we talked about membranes, we were talking about kind of what they are, how we describe them, how we set them up, how we understand where the flows are going. It's really the big important thing is to understand what's happening, right? How does water reach the membrane? What happens with the separation process? And also understanding the fact that they're not always going to be intuitive in terms of the way they're set up. So you might have, in this case, it kind of looks like you could have the permeate going across to the other side, and the other side being over here, but in fact, it's going across through this cylindrical membrane here and being collected out the bottom. So the shape of the membrane apparatus might be a little tricky sometimes, but just showing you that we can operate them in some way that makes sense. Okay, a little bit about what we make membranes out of and what kind of stuff can we remove. The overall design parameters for a given membrane is, well, what are we trying to use it for? Are we trying to remove just bacteria? Is that fine? We've got some other process to take care of viruses, or maybe some application that doesn't care. So what size of pores do we need? That will determine the pressure and flux limitations. Another design parameter would be the flux, right? What kind of flux can we use? Certain membranes can only handle a certain amount of pressure, so that plays in if we are trying to go such a small pore size, but we wanted to use some material for some reason, maybe we get into trouble because we have to put too much pressure on it to get the flux we need. So there's an interchange of these different pieces, the pressure and the flux being the main ones. Now, they can be a little more complicated, as we'll see. Maybe we have a tube, and then we take the surface area of the tube. Okay, what can we remove and how much energy does it take? How much flux? So, and by energy, I'm really meaning pressure, which would correspond to energy. We've seen a chart a lot like this before when we were talking about sedimentation, where we have conventional media filtration. This is our granular type of deal. This will remove particles, and this is micrometers here, or that. So a conventional sand media filter can remove things down to a little over a micrometer. And again, that's not necessarily the size exclusion, some of that adsorption and stuff. So we can maybe remove some bacteria with a conventional filter, but we're certainly not relying on it to get all bacteria. So if we take then a membrane and apply it with what we call microfiltration, really that's referring to what pore size do we have on the membrane? What size are the average holes? Now, again, if we have one big hole and a lot of small holes, you're going to let everything through, right? So it has to be not just the average pore size, but it's really the kind of the largest pore size of this membrane that's allowing water through it. So if that's in some range to exclude bacteria, of course, then we're removing bacteria. The operating pressure here, we'll notice this is given in kilopascals. So for a conventional media filter, it's about 10 kilopascals. For a microfiltration, it'll be between 10 and 100. And to put this in reference, 10 kilopascals is about 1 meter of water. So 1 meter of water stacked on top of a granular filter, or maybe you've got some elevation feeding into a membrane filter, kind of to do it with a lower energy or rainwater harvesting or something. 1 meter of hydraulic head is about 10 kilopascals. It's actually 9.8. You'll recognize that, acceleration due to gravity. So the connection there, right? So this means that with approximately 1 meter of water stacked up on top of the granular filter works. But maybe if that resistance doubles as we operate and it gets dirty, maybe it becomes 2 meters. So if you think back to those videos we saw of the water stacking up on top of these granular beds, that kind of tracks, right? You could see that maybe somebody could stand on one of these sand filters and you'd have these little troughs kind of maybe waist high or something, right? It would be, you could kind of get a feel for the fact that water was going to stack up on top of them, but not tens and tens of meters, right? It's a couple meters maybe. So that, hopefully you can kind of see how that's tracking. So we could operate maybe a large pore size microfilter around that range, or we could go up to about 10 meters of water, 33 feet or so, and that could actually power something that's getting into what we call the ultrafiltration range, which will start removing viruses. So if we think about like disaster relief or point of use filtration type of situations, if you can make a small water tower or store your water, with some elevation, you could actually use the gravity feed there to power a filter, a membrane filter that can even remove viruses. So that can be a pretty good option. You just have to hit all that at the right spot and have some way of getting your water to elevation, which may require power. Okay, so a few little kind of tangible things like that for you. If we go lower than that, we really want to remove small stuff, like even smaller stuff than viruses. So a virus is a large agglomeration of big molecules, is one way to think of it. A whole bunch of proteins stuck together, wrapped up in a little package. It's a large, they range from about 20 to 100 nanometers typically in like a diameter. So if we want to remove, let's say, just proteins, we need something smaller. That's when we're getting to the low end of ultrafiltration, and it's kind of a spectra here, where we go ultrafiltration, then we start calling it nanofiltration, then we start calling it reverse osmosis. It's a little bit arbitrary. Eventually the pores get so small that it's not actually very precise to say, oh, it's exactly this size hole, but it's how much, like what types of molecules can make it through. How heavy are those molecules that can make it through this membrane? Don't worry too much about that. The point is that as we get smaller and smaller, to reject smaller and smaller things, it's going to take more and more pressure. So you can see this ramping up by the time we are at, this would be 1 nanometer here, or 0.001 micrometers, or 0.01 nanometer. So it would take essentially an equivalent of 100 meters of water stacked up on top of that. That's actually a lot of pressure, right? So it's going to take a lot of pressure to feed these. And all the while, as we ramp up the pressure, we are ramping down the flux. So remember when we talked about the granular filters, the flux across the filter was the speed at which water is going across an area. So for the membrane, it's the same thing. The speed at which water is going across our membrane surface area If we want a high flow rate, we get a big surface area, but we also would like a high flux. So either way, what we see is that as the flux decreases down to 1 from up from like 100 at the microfiltration range, 100 times smaller with 100 times more pressure required. So it's kind of a square power type of a deal in terms of the amount of water we're getting per pressure, if we think of it that way. So, so as we go this way, higher pressure, and lower flux. And if we go the other direction, of course, we can get more flux with less pressure. So all that to say, we can do reverse osmosis. We can desalinate any water. That's always possible. But what is it going to cost? And usually there are more cost-effective ways to get clean water. So if you ever hear alarmism about we're going to run out of clean water, it's pretty much bunk. The deal is we need energy to collect that water and the infrastructure to do so, and a good way to discharge the waste salty water without harming the environment too much, right? So never buy into the scare about we're going to run out of water. It's actually an energy and infrastructure engineering problem. Okay, that's always going to be the situation if there is water of any sort nearby. We could take wastewater. How do people live on the space station? How do they get water? We're not shipping water up there every day, right? How do they flush? How do they drink? How do they? You get to start thinking about it. You realize there's some hefty water treatment on the space station. We'll say that because they're going to recycle every last drop. It's going to probably 1 liter of water would cost more than any of us are going to make in our lifetimes to get to the space station, is my guess. So that's an expensive ordeal. Anyway, so what kind of stuff do we make membranes out of? Well, there's 2 forms, polymeric and ceramic, meaning plasticky type of materials, polymers, or a mineral type, like a ceramic of some sort. So polymer membranes are kind of the more typical, more common. They're easier to manufacture. They naturally tend to be kind of flexible. So you can bend them, you can shape them, you can do things with them without breaking them. You do have to be careful because you don't want to scratch or anything the surface, but you can usually manipulate them pretty well. A few common ones, there are many, many more than this, but cellulose, PVC, PMMA, that's polymethyl methacrylate, all sorts of other ones, right? So you can get some bio-based polymers, you can get some just PTFE, you can use all sorts of things, and depending on the size, the pressure requirements, how you want to clean them, maybe some polymers are not susceptible to chlorine, so you could bleach the polymer to help clean it and get rid of some fouling, or maybe maybe not. Ceramic, they're a bit brittle, but they have some other properties that are pretty handy. They can be used with higher pressure because they're structurally much more sound. So if you can avoid breaking them in terms of the brittleness, they can handle high pressure. They're very chemically resistant because it's ceramics. We often use like a ceramic crucible or something to burn stuff, or a mug is typically ceramic instead of plastic, so that you can microwave it or pour hot coffee or do whatever to it. So you can make these that are chemically resistant. It takes a little extra effort. These are a little bit newer, and actually just a few days ago I saw some interesting news. Speaking of space and everything, apparently there is for the XAI, they are planning to reuse Memphis wastewater as cooling water. And so what they're going to do is they're going to use what's called a membrane bioreactor, and they're using ceramic membranes. So I've worked a bit with membrane bioreactors. It's a wastewater technology pairing the membrane separation with what we're going to talk about with the biological treatment. Wasn't planning to tell you a lot about MBRs, membrane bioreactors, but we'll get into it a little more. This is just a quick little article. I think plans were announced back in February, and then just the other day, they broke ground on this treatment plant. So these modules here, I think, is what they're using, and they're going to provide a pretty robust way to treat the water to the point where it's good to use it for cooling their power plant. Is their plan. That's pretty neat. I think that's the first time I've seen wastewater being repurposed for cooling water. And when you use river water or something for cooling water, typically you would need to treat it at least well enough so it's not going to gunk up your cooling towers. And then you're probably going to need to make sure that the temperature is fine before you discharge it, because it's kind of wastewater. We'll talk a lot more about wastewater very soon. Anyhow, I thought that was pretty neat. So check that out if you're interested. Now, how do we apply these? What kind of shape or form? We just saw one kind of interesting. It looks to me like these are, you can't roll ceramic, right? It has to be pretty much some sort of flat form. So I think this is a bunch of flat sheets just layered in there, kind of like that, side by side, and they've got it all set up that way. That's what it looks like. But if we do have something paper-like, I don't know whose papers these are, but we'll use it. You could take a flat sheet membrane that's got, I don't know, not quite a square foot, but we'll call it a square foot. And you could take another and maybe some more, and then as long as you do the plumbing correct, so make sure that water can only flow either across for the retentate or through for the permeate, then you could potentially wrap these and take all that, now we have 3 or 4 square feet of surface area in a little spiral wound membrane module. And that's exactly what is done pretty common. You see this at the picture here. And you notice when I say the fancy plumbing, there are spots where water can make its way through the interstitial spaces. They've got little separation things allowing water to flow. And then anytime you cross one layer of a membrane, then it's collected and it spirals its way down into the center of the module rather than traveling. So if we were feeding into the side here, if it passes through a membrane, then it's going to circle through this kind of extra porous support layer down into the middle and then be collected and be taken. Example. Another thing you can do is take tubes. We saw one as an example in that lab setup. And you have the membrane itself, or the separation layer, either on the inside of that tube or on the outside of that tube. And then you can operate it so that water can go from the inside and then go out, having separated across that inner lining of the membrane. Or you could flip that and say, well, if I have it on the outside, we're going to pour water through on the outside of it and force its way through across that tube into the tube, and then you've got your permeate. So it could be inside out or outside in. This is not an ultimate frisbee reference, but if you've ever played, that's a little shout out there. This actually matters a little bit because you have a difference in diameter, whether you're inside or outside. On the inside, you have a little smaller surface area, and on the outside, you have a little more, even with the same exact tube. So it's a little preferential to do outside in for the surface area, but maybe sometimes you want to just set it up in a particular arrangement. Now, when you are doing this separation, you don't want to have particles getting clogged inside the supporting area of your membrane. And I have some slides on that in a moment, but if you imagine that you have a membrane and on the top are the pores that you want to let water through. On the bottom, you actually want larger area, larger pores, and it's just a support network. It's almost like you're, I don't know, making a bridge and the surface layer is like that's where you want to stop the cars from falling through. But everything underneath it just needs to support that layer, right? Maybe you have, I don't know, some fancy concrete that lets water fall through or something. And then, the point is you don't care, and you don't actually want your particles getting stuck in that supporting layer. You just want them being there. So you want to operate this way and never this way. Does that make sense? Because otherwise that supporting layer just gets completely clogged up. Okay. All right, we can take that same concept and go smaller. These are called hollow fiber, or essentially what it is, it's microtubular membranes, and you can think of them a little bit like spaghetti. Is about the size of what we can make, where we can consistently make a good membrane surface with a very small thing. This is just a way to increase our surface area much more than these large tubes. Right? So if we take it, make them smaller, we get higher surface area. So you'll see hollow fiber membranes pretty commonly in practice. And they could be in a cartridge like this. Sometimes you put them in like a bag sort of situation where you're drawing a vacuum, pulling water through that, and anything that makes it in, through, into the tubes, you're pulling it out. Okay, so I've got an example problem here. I'm going to go quickly through it to show the setup. Maybe I'll come back and solve it with you, but I'm just going to try to speed through so we can get through more content today, like I said. Okay, so if we have a membrane filter that's used to concentrate algae for a culture analysis, it is a water treatment-ish type of a system, but here we are concentrating some sample. A membrane with a pore size of 0.45 micrometers is used to reject 90% of the algae. The filtration cell has a volume of half a liter, can be operated either cross-flow or dead-end mode. So if you stop and think about it, I've not told you anything about the math behind membrane stuff yet, but I'm asking you a problem. So you already know enough to do this problem, okay? So keep that in mind as we talk about this. It is a pretty straightforward ordeal, but you need to know about filtration to solve this one. So initially the filter is operated in a dead-end filtration mode. So that means we can go ahead and draw something, right? We've typically drawn a little syringe filter or something where we have our filter. If I can spell it right. Water will pass through that. We'll start with some amount. We were given that's 0.5 liters. We're given some concentration, initial concentration of the algae. I'm going to go ahead and call that N naught. 3.5 times 10 to the 5th cells per liter. Okay, the initial volume is 500 milliliters. That's half a liter. What is the concentration of algae in the feed if 450 milliliters of solution is passed through the membrane? Now, note that we are rejecting 90% of the algae that was given, and that means 10% will make it through the membrane when we filter that water, and then we're left with 50 milliliters of water, right? We pushed most of the water through, but we kept a little bit. So with all of that, you should be able to solve the problem. I'll give you 30 seconds. It's a good time to pause if you wanted to come back to this and do that. Think about how you'd approach this, and then I'll go through it with you. All right, So first thing I want to say is we're given a little more information than we really need. The problem described the membrane as a 0.45 micrometer. Like I told you, I didn't really give you any source of information about membrane-specific mass. So that's a membrane-specific number. We don't really need it for anything. It's just part of the context. So we're not going to use the 0.45 micrometers for anything. We weren't given anything about the size of the things. In fact, we were even given a rejection percent. So we just know, okay, some amount. So really, we just need a conservation of mass type of approach here. So we start with 500 milliliters, excuse me, and then we're going to end with 50 milliliters here, and we'll have some n, I don't know, nu that we want to solve for, right? So what we can do is we can take the 450 milliliters, or 0.45 liters, and say, well, how many cells were in that, and how many cells left? Actually, what I should probably do is we'll come back to that. We'll say how many cells of algae are in solution. And then all we have to do is divide that by the remaining water. This will give us the new concentration. Okay? So all we have to do is figure out how many cells were there in the first place, subtract how many cells left by making it through the membrane, and then divide it by the remaining volume. Okay? So the cells should be equal to the initial minus the escapees, and then if we divide that by the new volume, we get a concentration. Okay? So the initial cells, we were given 3.5 times 10 to the 5th. That was per liter. So we have to multiply that by 1/2 because we have half a liter. That should give us, what, 17.5, 1.75 times 10 to the 5th cells. Sorry. Then we need to subtract how many left. So the number that left, the escapees, this will be that 450 milliliters times the 10% times the concentration that was in that to begin with. So we can say this will be 0.45 liters times our 3.5 times 10 to the 5th times the 10% that made it through. So that turns out to be, I don't know exactly, but it's kind of close to 10 times less than this guy. So it'll be something times 10 to the 4th cells. Probably slightly less. It'll be like 1.7-ish. We'll go ahead and do that. So 15.75 times 10 to the 4th cells. Yeah. Yeah, so yes, thank you for the question. So I skipped over a little bit there. So if we are rejecting 90%, that means 10% are not rejected by the membrane, meaning 10% of them pass through. So that's the key, and I totally glossed over that. We will actually formalize some of this with a few equations that I'm giving you in terms of rejection, fraction, things like that. But I wanted to show you that you can actually solve this type of thing just by understanding what's going on and what's going where. Right? It's a mass balance approach, but you do, yeah. So this means that 10% escape. or make it through the membrane. Okay, so rejection means that they are not allowed past. Okay. All right, so then here we have the 1.75 times 10 to the 5th minus 1.575 times 10 to the 4th. And then we're going to divide all that by 0.05. Just going to do this in Excel real quick. All right, so we had 1.75 times 10 to the 5th minus 1.575 times 10 to the 4th. And then we're going to take that, divide it by 0.05 liters. Let's just go ahead and make it easy. Come on.
So we're essentially trying to find the concentration of algae that's in the is it the permeate, the clean water that's supposed to be coming out?
What does the question ask?
So it's
What is the concentration of algae in the feed if blah, 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 right? So we're looking for the concentration in the feed, not the permeate. We could solve for the permeate, which should be 10% of what we started with, the starting concentration. Does that make sense? Okay. All right, so we had 3.19 times 10 to the 6 as a final answer. Got to divide this by the 0.05 liters. All that, the N nu becomes 3.19 times 10 to the 6 cells per liter. Now, if we stop and think about it, we concentrated almost all of the solution. We took almost the whole half liter, passed it through, and it's keeping almost all of the cells. So without even thinking any harder, we might say to ourselves, well, we removed 90% of the water and kept almost all the cells. We should have about 10 times the concentration. A little bit of loss, and we didn't do all the water, so, but we got rid of 90% of the water. So it should be about 10 times. So if we had 100% rejection, it would be exactly 10 times concentrated, right? And we almost didn't even need math for this, right, to do all this stuff. So I wanted to show you that if you master the what's happening here kind of aspect of this, it can become very intuitive and very straightforward. So here, if we take a look, we started with 3.5 times 10 to the 5th, and we ended with a little less than 3.5 times 10 to the 6th. So 3.2-ish. All right, so that's kind of the point of this problem. Now I have that highlighted, the percent, because you could play with that, right? You could do your own problem, change that. You could change, all sorts of different things here. But what if 100%, right? Then you can see what I just talked about. What if 10% were rejected? How does that change the numbers? Okay. Any other questions? Yeah.
Like when you solve that, you move over, so you divide by the 0. Why do you divide by the 0.0?
That's the amount that's remaining in the feed. So there's a new feed volume. It's a great question. So this is the initial feed is half a liter, and then 0.05 liters, that's the 50 milliliters remaining after we passed 450 through. I also glossed right over that one, so that's a really important point there. Right, so if we pushed 450 mils through out of the 500, then we're left with 50 remaining. So this would be like the new volume.
So that's the initial minus the escapees that are in there.
So what I did was I took this volume here, that's the initial, well, let me just write it this way. I'll say V initial minus V permeate. So it's the initial amount we had minus what we pushed through the membrane. So it's just the V remaining. Yeah. So in this situation, we are doing dead end. We have no retentate aside from the feed that is still there. So that's exactly what we did. We could find the concentration that permeate, but it's rejecting 90%, so it should only be 10% of what we started with. Yeah.
If you were to do a couple of these in series, you would just use the concentration of the permeate as like your initial concentration.
Yeah, so typically if you ever have a sequence of membranes, we don't often do like the same exact membrane type in sequence. I guess maybe sometimes you would, but usually what you'll do is you'll go finer and finer in terms of pore size. So you would take the permeate from this one and then pass that through a finer filter now that you've removed the larger particles that could damage the next one. That's a good question. All right, I'm happy to answer more questions. I'm going to go ahead and pull up the next set of slides. Which also start where that one ended. All right, anything else? You got it? Okay, so let's put a few formula to that type of thinking. And we'll go a little beyond it as well. But we'll start with a solute balance. We just did a problem where we took a look at what was dissolved solute or what was in the solution. If we want to define the fraction rejected, we can describe that as 1 minus the concentration in the permeate divided by the concentration in the feed. So this would be the permeate, and this is the feed. So just like we were seeing a moment ago, the fraction rejected would have been 1 minus what's in the permeate was 10% of what's in the feed. So this would be 1 minus 0.1 is 0.9. 90% rejected, 10% passing through. So this is a formalization of what we just looked at, right? Capital R being used as fraction rejected is 1 minus Cp, the concentration of the permeate, divided by Cf. This would hold true for a cross flow, like a continuous flow system with the concentrate as well as the feed and the permeate, or also held true in our example with the dead end filtration. Now we could take a log of this and call it R log. Sometimes that's convenient if we're talking about like 99.9% rejection. So if we had, for example, if it was 99.99% of algae, we could do that same exact problem with that value. And in this case, the fraction rejected is a little uncomfortable to write every time. It's 1 minus 1 over 10,000, or 0.99999. We could just call that R log is 4. So it's rejecting 4 logs of the cells or the viruses or whatever it is, the algae in this case. Because if we take the R log as defined as log of concentration in the feed over the concentration in the permeate, essentially what we're saying is how much more concentration is in the feed compared to the permeate. That's going to be a big number if we're rejecting a lot. And so if we take the log of a big number, we are, taking the log of it, right? It's we're essentially deriving how many times, how many factors of 10 are required to get there. So if our feed is 1,000 times more concentrated than our permeate, that's a 3 log removal, or an R log of 3. So just some fancy terms, ways to describe it. And usually we're targeting for something more than just 90% removal. Usually we're trying to say, hey, we need to use this membrane to really make sure that the water is clean to drink. So we're going to aim to get 99.999% of viruses out, right? We might be okay letting 1 in 100,000 as a kind of a standard. Okay, so on a water balance, so that's a solute balance. Water balance, we'll use a lowercase r. By the way, I have some materials. We don't have a whole lot in our book itself for membrane stuff, but I have some other materials if you're interested in further reading. Happy to supply some, and I think there's some on Moodle under this section. If not, I'll double check that. But so I'm just following the kind of typical conventions here with the R's. Sorry that there's multiple R's. The lowercase r here, we're talking about water recovery. A lot of times we will be interested to know how much water are we processing and recovering from our system, given that we often have to, at least in the continuous operation, lose some water for that concentrate stream. Of course, we could flip that if we're concentrating something on purpose, like we talked about orange juice or something, or the algae. Maybe that's different. Anyhow, this lowercase r would be the Q in the permeate divided by the Q in the feed. So what's the portion of the water that we are using becomes clean water. So we could think of that as the clean versus the feed, or the permeate over the feed. So if we have a system that is keeping 85% of the water, our water recovery rate is 0.85, or 85%. That means 15% of it would be going to waste. Right, that's the example down here. Okay, with that, we can calculate a few things. And this is also kind of on the basis that we know that a total flow rate that we're delivering to the membrane, QF, is going to be equal to the two streams combined, right? QR plus QP. Again, we can draw a generic membrane system, something like this, where we'd have 3 arrows, where we have a feed, a rejected stream or retentate. It did not make it across that line, and a permeate. Right, so each one can have a Q associated with it, and we're not losing or creating any water otherwise. All right, so flux, we've talked about it in the sense of granular filters a bit. So it's a very similar concept. We're going to go a little fancier with it for membranes. If we describe flux as J, as flux across a membrane surface, we can describe this in some similar terms of a volume per area per time. If we put the liters here, we could put it cubic meters instead of liters per square meter per hour in this example. We would see that essentially this also becomes a velocity type of a term. Of course, it's volume per area per time as a whole, but that can simplify to a velocity. And then that would make sense if you say, okay, what's my velocity passing through my membrane? All we need to know is how big the membrane area is to understand how much we're really treating, right? Okay, so we could also describe this as J equals the QP, Q permeating, the Q that's making it past the membrane, divided by the surface area of the membrane. And keep that in mind. If we are doing the filtration, we have to use the flow that is making it across the membrane for the flux, because it is flux across the membrane. AM then would be the surface area of the membrane. And of course, like always, our flow rates are going to be consistent. So if we have some information about how much water we are feeding the membrane and a ratio, maybe the water recovery rate of the membrane, then we know exactly how much Q is permeating. We will be able to solve that. All right. So another example problem. This one, I think I will describe the process and let you do it on your own. It's pretty straightforward. It's actually mostly geometry problem. Okay? So I'm going to read it for you. And you're welcome during the exam review if you'd like me to solve this with you. We can certainly come back and do it. So here we have a comparison of an outside-in and inside-out filtration. So remember, we're dealing with some sort of a tubular type of situation. And we have a Dow FilmTech membrane module containing 5,760 fibers. The fibers have some length, 1.87 meters long. So these are long, thin fibers, hollow fiber membranes. And they have outside diameter of 1.3 millimeters. And an inside diameter of 0.7 millimeters. We're given a flux of 75 liters per square meter per hour. So we can say J is 75 liters per square meter per hour. And we have two ways of operating. One would be the outside in, and the other would be the inside out. So in this case, maybe the outside and the inside are both separation layers, or maybe they're just deciding on which one to design. I don't know. The question then says, calculate the water production from one module if the flux is that, and we do either inside out or outside in. So when it says calculate the water production, and we're not given over some amount of time, I think we're really looking for a flow rate. And we'd be looking for the flow rate of the permeating water. So we can relate that to the flux. We can say the flux is equal to the QP over the area of the membrane. So in order to solve for our QP, what we need is the flux that was given times the area of the membrane. Now, we have a module of many of these membranes, many of these fibers, right, each with membranes. So we have a total membrane surface area that depends on the geometry of how we solve the cylinder, right? We need the surface area of a cylinder. So to get the area, so in one, this is outside in, and this one's inside out. So we're going to solve for two different areas here. I'll just say solve for the surface area of one cylinder using, in case one, the outer diameter, or for case two, the inner diameter. And once we have that, multiply by the 5,760 fibers, and then solve for our Q. All right? So it's just a little bit of geometry. Need the surface area of a cylinder should be the circumference of that circle times the length, right? So the surface area would be 2 pi r, or pi times diameter, times length. Okay, put all that in meters would be good, and then you can pretty much solve the problem. All right? Okay, like I said, you can either ask me to solve it for you with you during the exam review, take a look at the old notes of membrane filtration, second lecture for this class, or ask me. But I'm going to leave it up to you to do what you need there. I really think that one's pretty straightforward. It's geometry. Okay, I want to get to a few other topics. So pressure that drives the membranes. We can relate the pressure to some of the membrane parameters. So when we think of the pore size of a membrane, we already talked about how if we restrict the pore size, it becomes hard to push water through it. And so we kind of need to know how to work with that type of a calculation, how to work with what's called the membrane resistance, what happens if it starts getting dirty and fouled, and how can we handle that. So if we define the pressure required as the transmembrane pressure across the membrane, we have high pressure in front of the membrane, pushing on the membrane. On the other side, water comes through and it's lower pressured. Okay, that's how it works. So you can imagine that there is a pressure differential as the driving force, pushing water across it. We can mathematically describe that as, or we call it TMP, as the pressure in the feed minus the pressure in the permeate. Okay, it's just that difference. So we had a question earlier about multiple membranes in series. You could actually have a really high pressure system, but only a small pressure drop over a first filter. So the feed has, let's say, 1,000 kilopascals or some whatever pressure unit you want. And then 900 kilopascals in the permeate, so it was only a 10% pressure drop, so that the remaining pressure can drive another membrane requires more pressure. So you could set these up sequentially, and any given membrane can really probably only handle a certain level of pressure differential there. That would be the deal. Okay, we can define a flux in relation to the transmembrane pressure, and that will give us some concept of, okay, this flux, which we already have another definition of it, the Q, the flow rate divided by the area. Well, we can relate it to how much resistance is the membrane providing. And it's not just the resistance, we also have the viscosity of the water here. So if we were trying to filter honey, it would be a lot more difficult, right? If you look back on our table of viscosities, you'll notice, hey, we could also potentially heat up our water, and then it's easier to filter. So at some point, actually, speaking of ceramic membranes, I had a fellow grad student when I was in grad school doing a research project on ceramic membranes for cleaning up power plant, like a flue gas capture water. So it was hot water, and you needed a ceramic membrane to withstand the heat, because most polymers would kind of get too squiggly or melty or whatever, would degrade. And the water itself is less viscous. It's not super viscous to begin with, but if you heat it up, you'll see that number is dropping. So it actually becomes easier to filter. You get a better flux. Anyway, the relationship here is the transmembrane pressure divided by a RT, that's our total resistance of the membrane, times that dynamic viscosity. The flux has to end up with the same units as we normally have, some sort of a flow rate, or flow rate per area, essentially, volume per area per time. So we're going to keep our resistance units in per meter. So it's kind of like how much resistance is there in a meter of this membrane. We never have a meter of it in terms of like distance water traveling through it, but it's convenient to stick with meter units. That means we can use pascals for our pressure. That relates us to meters and kilograms and all that. And that means our dynamic viscosity, which we relate in kilograms and meters and seconds. All of that fits together nicely so that our flux, according to this equation, will be in cubic meters per square meter per second. Okay, so if we have those units set up, this is what it will be. And this resistance number, if you think of like, I don't know, something like a portion. How much more effort does it take to go through this really, really thin membrane? But then we're talking about as if the membrane was 1 meter, so it's a per meter unit. This is going to be a very big number, just naturally, because then we're going to say it's not actually a meter, it's like, less than a millimeter for the real distance it actually has to go. So this is a large number, and that's just the way it is. Something like 10 to the 12th per meter. So we'll just see large numbers there. That's just normal. It's just the way it is, okay? It's a good thing we don't make our membranes 1 meter long. So I mentioned earlier and used a poor analogy to try to describe this, but if we take a look at how a membrane is structured, we have a separation layer, and we can kind of see this very thin or very compact spot. Maybe this is a better view of it, where our separation layer has very small pores. And then below that, we have larger pores, and this is just the supporting layer. It's usually a bit thicker. We have to find some way of keeping structural integrity of that very, very fine small pore area, but otherwise letting water through with as little resistance as we can manage. So the limiting resistance is usually going to be the separation layer and or any fouling that accumulates on top of it. I like this image here. This is a really good view of it. It's so fine on the top where you can kind of feel like nothing could pass through it, but you can kind of see water would pass through down there. So as you can see just from this slide, depending on what we're making these out of, they can look very different, right? We can have different sizes, we can have different structures. And over here, we'll talk more about this in a second, but you can also imagine if we have particles that are being separated, they start accumulating, and we get some, what we might call a cake layer of fouling junk. And then the fouling junk will separate smaller particles because it's accumulating and blocking stuff. And then we have some fouling layer that's actually also doing filtration. There are a few cases where people actually design a membrane such that it accumulates some fouling stuff and then uses that fouling layer to do the filtration. That's not very common. Usually we're trying to avoid fouling and shake it off, wash it off, backwash it. And membranes, if we backwash, which most of them do, it's a very quick, small spurt. We just reverse the flow for a moment and shake everything off that we can, and might go a 10-second or 20-second backwashing cycle in every minute of operation, or every 10 minutes of operation, something like that. So depending on the design, depending on the scheme, that's going to change a fair bit. But and we don't usually worry about that quite as much when we do our calculations as we did with the granular filters. That's a bigger process, a lot more water to use. It's a lot more complicated than just simply reversing direction for a moment and shaking stuff off. We also have in membrane filtration, we're also going to have that retentate stream in the first place, where we are already always wasting some water, and that backwashing is just going to get caught up in that. So we don't really have to worry about the math in the same way. Okay, so that's kind of what they look like. I left my previous drawings here. I'd like to think that I did that on purpose, but I don't know if that was on purpose, but nice little drawing there on the side, because I want to describe the different forms of resistance we can get. The RT would be the total resistance of our membrane. Anything that's resisting the flow of water is adding to that total resistance. So that's what goes into our flux measurement from before, right? It's RT here. Total resistance of anything that's resisting the flow in the membrane. But we could describe that as a few components. One would be the membrane itself. Small pores, going to resist the flow. But then we could also have some fouling resistance and distinguish that from fouling resistance in a cake format. When I say cake, I'm talking about particles that are accumulating to a large extent here, right? So what I'll do is I'll highlight these colors. So if we form a bunch of stuck particles on the surface to the point where they're building up a cake, and by the way, the water would be flowing something like this, where it's trying to go across the membrane. So this would be the QF, this would be the QP, and Q retentate. So if this is kind of the scheme and we get a cake layer formation, in our diagram here, we've got that separation layer on the right, then any resistance to flow that's coming from that layer of excess fouling will be right there. So if we can knock that away with backwashing or something, we could lower the total resistance of our membrane. And that would be a good thing. There's another type of fouling, just generic fouling, I guess, that we could describe as particles that are getting stuck kind of in process. So along the way on any part of the pores, inside the membrane, on the pores, not the cake, but just adding texture and slowly constricting the pores. So these are all this stuff here, kind of on the inside. That's what we're talking about. So that's a little harder to clean. Maybe this is where we might want to use chlorine or something, or an acid wash or something like that to try to dissolve or eat away anything that we can. You know, a ceramic membrane you might be able to pour drain cleaner on it and it's just gonna zap any of the organics. A polymer membrane, you'd probably be ruining your membrane in a split second. So, all that to say, membrane cleaning is quite important, and if you ever work in the field, you'll see many times you'll see people try to restore the flux back to a nominal starting point as if it was a clean membrane. Like that's kind of the target. Can our cleaning cycle get us back to normal? Can we operate, watch how it drops, the flux or the pressure or whatever, however you want to measure it. Can we bring it back up to kind of a clean status? Okay, so all that to say, we can describe membrane resistance in a few ways, or a few components, but ultimately it just goes into how much resistance is opposing the flux. Okay, and then it's in the flux equation. And these membrane resistances are just additive, effectively. All right, one last concept for us here is membrane permeability. We have a term LP for this, and this is essentially the flux divided by the pressure. It's obviously very related to the what we were just talking about, and if we recognize that our flux has some dependence on the transmembrane pressure and RT, the total resistance, then we'll recognize the permeability also has to do with the resistance of the membrane. In fact, the pressure terms kind of cancel, so we're left with permeability being a function of how permeable is the system. Duh, right? How big are these pores? What's going on with that? There are permeability studies you could do in soils for water flowing through soils, Darcy's law and all that. It's a very similar concept. We can just, for the sake of our memory, say this is going to be J divided by the transmembrane pressure. Another diagram here to add a little extra texture to our fouling. We can describe it a few different ways, where we have complete pore blocking, where a particle would get stuck and block the pore entirely. Cake filtration, where particles kind of are getting stuck because it's acting like a filter by itself, the fouling layer. And then the generic fouling is something like a combination of the standard blocking and then maybe before we're quite getting a full cake. Don't worry yourself too much with that unless you are aiming to become a membrane operator, then then you might be a little more interested. Yeah.
If the permeability is the flux divided by the TMP, can you just simplify the equation by just saying it's equal to 1 over RT times the viscosity?
Yeah, I think so. So LP RT, let's just double check that that works out, but I think that would be true, because we said flux was TMP over RT times the viscosity. Yeah, I think so. Okay. Any other questions, concerns? All right. Got another example problem. I think this one might even, is this one in your homework? I don't remember. I think what I'm going to do is I'm going to walk you through the basics of this one, then we're probably out of time. So like that previous problem, I know that I have discussed this before live, and we could work on this together if you feel the need. It should be relatively straightforward, and I'll kind of guide you through the main steps here before we let out, and we'll just have to do a quick session on disinfection next time. Might have to come back and give you a little more context or flavor for disinfection later, because it's kind of my favorite topic. So I've left myself with not as much time for what I like to talk about. Anyway, so here we have operators for a small groundwater cleanup. They're going to do a cross-flow microfiltration membrane as a pre-treatment step to ensure the influent groundwater does not contain large particles, which can clog up some other treatment. The system must treat 200 liters per hour. It utilizes a membrane with a pore size of 2 micrometers and must recover at least 95% of the water. The influent water contains 30 milligrams per liter of particles, and the membrane rejects 85% of them. So we're given a lot of info there. And first up, it says the system must treat 200 liters per hour. If I was thinking this is a production for use, I would think to myself, okay, we have to meet a demand of 200 liters per hour. Like someone's going to use 200 liters. But the context here is a little different. We're treating some wastewater, or like a cleanup type of water. So that's actually probably the feed that we're talking about with that 200 liters. The other part that's giving me that hint is it says it must recover at least 95% of that water. So, okay, that really tells me this 200 liters should be the feed. The problem's not great, and I think I wrote it, so that's my fault, probably. Or at least I could clarify. But I'm led to believe that the best approach would be to say that would be the situation. So other things we know, we have some concentration in the feed. That would be the 30 milligrams per liter. We know we have to recover, or so we have to have a rejection. So particle rejection, that would be the uppercase R. This is 1 minus the CP over the CF. This has to be at least 0.85. So we could say we know that the concentration in the permeate can only be 15% of what's in the feed, based on that. We have to recover at least 95% of the water. So if our water recovery is the Q in the permeate divided by the Q in the feed, that has to be 0.95 or better. Okay, I think that's a few pieces of information that we're taking a look at. By the way, now that we've talked, I've given you all the formula that we're going to use about membranes, talked about them. I hope that you have some recognition of what's relevant in terms of pore size, in terms of practicality. And that might be something I could ask on like a more topical question. but we've not done anything that relates pore size directly to permeability or anything like that. We're just not going that deep. That's certainly something that could be done, but we've not talked about it. So when we see it in a problem, like a word problem, that's just extra info, okay? We haven't even related it to how much stuff is rejected. Maybe that's something that you could do, but we're not going to go there. Okay, anyway, first up, label the feed, permeate, and retentate. So A would be the feed. What makes it across would be the permeate. So D or C would be permeate. Doesn't really matter. I'll just do that, and we'll say this is permeate. And the stuff that does not make it across is the retentate. Okay. Then part B, what is the concentration of the particles in the permeate stream? We kind of recognize that we have some relationship here. We can take these two parameters to solve for that, those two facts or relationships. What is the concentrate in the retentate stream? We don't have anything directly, so we just need to do a mass balance, right? Conservation of mass. We know that what we should be able to say is what's going in is equal to what's going out, right? We should be at a steady state, so we could write it up like that with no reaction. 0 equals Q in minus Q out plus no reaction. So that's just a matter of 1 Q in and 2 Q outs. And we know something about that Q out through the permeate, which will tell us what's Q out in the retentate. So we could say something like QF CF should be equal to QP CP plus QR CR. All right? And you should then have enough info to solve the rest of it. So the mass balance strikes again, but in a very simple form. So then part D, if the membrane is rated for a flux of 25 liters per square meter per hour, what is the total membrane area required to meet the demands? So we have a flux. We said that's going to be equal to a Q permeating divided by area of the membrane. We need to solve for the QP. We know that's going to be QF minus QR, just as a, QF is the total flow in the system, so QP has to be the total minus the other one. So we can get, we can use the relationship of QP over QF at 0.95 to solve for that, and then solve for, so we'll solve for QP, then for the area of the membrane needed. Right? Might be some unit conversions necessary, but you can do that. All right, process-wise, is feeling okay? All right. I think I just left some room to solve each part. All right, so we have 5 minutes. I'm just going to go ahead and let you out. We will talk about disinfection in a hurry next time.